So let's look at the analysis of the Grover search algorithm. So recall that the Grover search process can be looked as rotation on a two-dimensional subspace. So let me draw that subspace. So we have this is our solution space psi s. This is the orthogonal complement in this subspace. And the initial vector is the vector psi, which is the uniform superposition of all possible vectors. And this is our angle theta over 2. So psi is 1 over square root of n summation over x. This is our vector psi. And then the angle theta is such that sine of theta over 2 is equal to square root of m over n. And we assume that m is much smaller than n, where m is the number of solutions and n is the number of items in the list. Right. And the Grover operator is a combination of two operators, one which reflects about this vector, and the second one reflects about this, resulting in a rotation. And so in every iteration, we move the vector by angle theta towards the solution space. So this is angle theta, right? So now the question is, how many iterations do we need to get close to this solution space, right? So theta is given by this equation, and one can do the expansion of theta. So the expansion of theta looks like this. So theta is equal to 2 over, so I'm doing an expansion of theta now. So expansion of sine inverse of x essentially over n plus 3m over n 3 over 2 plus something which is order 1 over n square. So now what we'll do is take the first order approximation to theta. So my rotation angle, so angle of rotation, I will choose as 2 over square root of m over n. So we'll ignore these terms. And what does applying G look like? So G acting on psi is equal to square root of m over n sine of theta plus theta over 2 plus square root of n minus m over m cos of theta plus theta over 2. So one rotation will move by angle theta towards psi s, the solution space, and t rotations. So t rotations will be equal to square root of m over n sine of t theta plus theta over 2 plus square root of n minus m over, this should be n over here, n cos of t theta plus theta over 2. Right, so the idea is to get as close as possible to the solution space, maybe somewhere very close over here. Right, so that is where we want to go to. And we choose the approximation of theta to be theta is nearly, so it's a little bit lesser than what actually we should rotate. And the number of rotations times theta. So if I take t to be the final number of rotations, then this equation should hold. Um, t times, so t times each rotation is by 2 into square root of m over n. And then initially we have an angle of rotation, which is um, what we can do is we can write t times the rotation plus theta over 2 should eventually be, that's the ideal situation that we want, right? So initially we have this angle theta over 2, right? And then t times theta will, the ideal situation is t times theta plus theta over 2 is equal to pi over 2. And so the number of rotations is equal to pi over 2 theta minus half, right? That should be the number of rotations. But the problem is that this may not be an integer. So what we do is that we choose an approximation, which is an integer. So we take the actual number of rotations to be pi over 2 theta. This is the largest integer, which is less than this value, right? So, and we approximate theta is 2 over square root as the first order approximation, right? So, this will be the number of rotations. So how many rotations or how many applications of the Grover operator we need? We need t is equal to, substituting theta over here, pi over 4 into square root of n over m. So that's the number of applications of the Grover operator, and that's where this order of square root of n um, complexity for the query complexity of the Grover search algorithm. Right. So since we have chosen theta to be this value, whereas the actual expansion is this, and these are all positive terms. So what we are doing is actually rotating by an angle which should be less than the ideal angle that we should be rotating by. Right. So eventually we will hit a little bit less than. So we will hit, we won't hit beyond the pi over 2. We won't go over here. This is not the case, but rather we'll go over here. All right. Now, we want to also figure out what is the probability. So after we do these rotations, right, we will measure. And we also want to know what is the probability of success. So what is the probability of, so that will be given by, so probability of success. Once we have done these many rotations, it will essentially be psi s gt psi. Right, that will be the probability of success. Now it turns out that we can use a little bit of nice mathematics to show that the maximum angle, so the difference between the ideal uh, solution space and the the angle, the final vector that we have rotated to, this can be no more than theta over 2. This can be shown. Okay. So that means that the probability of success, this is going to be equal to greater than or equal to sine square pi over 2 minus theta over 2. Okay, so this angle, so it cannot be more than that. Okay. So once I measure, the probability of success is going to be the sine square pi over 2 minus theta over 2. And this is equal to cos square theta over 2, and which is equal to 1 minus m over n. Right? So success probability of the Grover search is greater than or equal to 1 minus m over n. So that is the analysis of the Grover's algorithm. Our complexity, query complexity, is order of square root of n. Once I apply pi over 4 into square root of n over m, applications of the Grover operator. So these are the Grover iterations, number of Grover iterations. And this will lead to a success probability of at least 1 minus m.